All right, so for problem 3, what I have is Earth and Mars are coplanar, so I don't have to worry about any inclination. The distance of Earth from the Sun is 1 AU, and the distance of Mars from the Sun is 1.524 AU. Mu of the Sun is 1.327 times 10 to the power of 11. And then, of course, 1 AU is equals to 149.6 10 to the power of 6. I'm using, of course, all kilometers and stuff. Now, what is the delta F for the transfer? Now, the initial F of Mars is 40 degrees. I'm going to keep on the side. Now, the idea is while the uh, satellite takes 183 days to fly to Mars from Earth, Mars is also going to move. Because while it's here at initial position 0, after 183 days, it's going to be at this point here. So we have to calculate what is the change between these two. Now, fun enough, the Earth is here and it's going to be on the other side. It's at apoapsis and periapsis, technically circular, but it's going to be at opposite side when the satellite reaches the other side, because 103 days is about half of a year. So it's going to be on their side. So you make sure your calculations fit there as well. Anyhow, so how much does Mars move? Well, if Mars moves, it's going to be 183 days divided by the period of Mars, and this gives us the fraction of this arch over the entire orbit, and then we can just multiply that by 2 pi to get the total F. Well, this is going to be delta F technically, so I can just keep it as delta F here. And then if I want to find F1, or when the satellite reaches Mars, I'm going to have to do the F naught plus my delta F. Okay, this ends up being 2.371 radians. Okay, now in order to do a Lambert's problem, I need, of course, to find the K, M, L, and P, little L, from what I have. Now, turns out that P has two values. It can either be a plus or minus. In order to find out whether we're in the plus or minus, we need to calculate plus or minuses for both our A max. Oh, by the way, A minimum is simply going to be the minimum energy transfer orbit. So 1/4 R1 plus R2 plus the square root of R1 squared plus R2 squared minus 2R1 R2 times the cosine of delta F that we just found, of everything divided by 1/4. Okay, and then we're gonna set an A max to be equals to 2 times A minimum. Now we're gonna find the P for both A minimum and A maximum. Once we find A minimum and A maximum, we understand which one is on which side. So in our case, we're gonna get, I believe, something that says that well, we're gonna find the P, of course, for each one of these, and then from these we end up getting, with Lambert's formulas, all the time of flight. Right, with if the orbit had these two semi-major axes. Now we end up finding that the time of flight for the Amax is going to be less than the time of flight that we actually need, and it's going to be also less than the time of flight for the Amin. Now, this is because they actually can take different paths to get to the same point. So for Amin, we can go this way, but for Amax, we can go this way. So there's many different ways. You just have to actually calculate these values here so that you can actually put Amax and Amin in the correct order. So it means that we're going to have an Amax here, an Amin here in our array, our A average, which is the sum of the two divided by 2. And then we need to find where does TOF lie, on this side or on this side. Well, at that point, we calculate the the time of flight for our A average, and we determine is it less than the time of flight or is it more than the time of flight. Oops. Now, if it's less than time of flight, it means it's going to lie on this side, TOF. So if it lies on this side, now what we have to do is we have to define a new A average. The way it works is that we take these two, A max and A average, and then this A average ends up being an A min on this side, and we define a new A average on this side. Now, of course, I'm not saying that A average is going to be on this side, but we need to just have it on this side. And then we find out again, is the time of flight at our new A average less than time of flight, or is it more, greater than, or is it less than the time of flight? And then we do it again. Oops. So in this case, we're going to take this. Our new time of flight will end up being our A average will end up being our A max. And then we're going to find the new A average, which is in here. And we're going to find the time of flight for this new A average. So TOF for A average. Okay. In order to do this, we're going to have to put some if statements in our code that detect is our time of flight on the left side or on the right side of our time of flight for the average axis, average semi-major axis. And therefore, then we have to cut down on the space in between the two of them by repeating this process of setting one boundary, keeping one boundary from before and setting the other boundary as the new time of flight from the semi-major axis average, which can be either on the right side, in this case it would be on the right side here, or it can be on the left side here. So at least for what I did, I'm gonna do it. I'm gonna show you what I have with Python. Okay, decided to freeze. There we go. Paste. As you can see here, I put, first of all, I calculated the difference between the time of flight that is the true one and the time of flight that is calculated, make sure it's in the same units, and then I put a margin. If the error or the difference between these two, I put absolute value just because it keeps just the error. I don't know, it just keeps the error, not anything else. If it's more than a margin, for example, it's our tolerance that I set to e to the power -9, then you can ignore this stuff here just for some plotting later, but you don't need to do it. Then, if the time of flight calculated was less than the time of flight margin, therefore you have this thing here. So you have A max on the left, we said. And then you have your time of flight calculated, that is, I'm going to put CA for calculated here, is less than time of flight. And then you have the A min on this side. Then this part here is supposed to be your A average, time of flight from your A average. Now your new axis will contain this. So on the left side, we're gonna have the time of flight that we have here, and on the right side, we're gonna have the A min. So it keeps doing this, and then we're calculating a new A average that is going to be positioned in here. And then, of course, I recalculate the time of flight for the new Lambert, just the Lambert function. It contains all the calculation I need to do. However, if the time of flight is greater than the real time of flight, it means that we have time of flight on the right side, CA, then the time of flight. Then we need to do the opposite because we had our A min on this side and our A max on this side and our A min on this side. Okay, so we need to do this now. Make sure that when you're doing with the MATLAB, you start from 0 because you start from 1 because as you can see here, I'm taking the 0th index of my list, which doesn't exist in MATLAB. Anyhow, as I say, so here now you have to take these values here now. So again, as you can see, your Amax will stay the same. Your time of flight calculated will then be equals to your A min here, and you're gonna find the new AAV, and then your TOF will lay in here on this side, the other side. So you just keep going on and on until you find it correctly. If you're interested in seeing what a error graph for this should look like, I'm gonna copy it here. Of course, the iPad froze when I asked to do this. There we go. This is supposed to be the error that you get from here. Oh, an error graph. So I'm gonna just start on the left side. Sorry, on the y-axis you have the error in hours because I'm calculating everything in hours. You calculate everything in days. That's fine. And on the bottom I have iterations. As you can see, the more iteration I have, the lower the error becomes. Okay. And my final value for A is equals to 195206672, so more or less those values. And then for my eccentricity, which then can be calculated by doing 1 minus P over A. P is the P that you calculated earlier, ends up being 0.235234, blah, blah, blah. Anyhow, well, actually there's a point here. So, anyhow, so this is how you find E. To go back, no, you have to make sure to pick the right P. And in our problem, the P that is the one that we use is going to be the one with the plus, I believe. Let me just make sure. Yes, yes, the one with the plus in front of the square root. So make sure you use that, and then you can iterate over and over.